Good morning, everyone. We're team 88. We have team member Jack, me as Max. We have Xiaohui and Xiao Yang. Our project is focused on vehicle detection. So what is the vehicle detection? The definition and the purpose is defining and locating vehicle in images or videos and used in traffic monitoring and autonomous driving, parking systems, and surveillance. And then we're going to focus on deep learning advanced, which is CNN-based objective detection models like YOLO, SSD, Faster R, CNN, which is high accuracy and real-time detection for the vehicles. So overview of our project, we classify images as vehicle or non-vehicle using deep learning models. And the approach is binary image classification using CNN-based models. The application will be supports traffic monitoring, autonomous driving, and smart city infrastructure. The performance of our project, we're gonna primarily using the accuracy, which is measuring overall correctness, precision, minimize the false positives, recall, catch all vehicle under the partial occasions or low light, as well as the F1 score to balance the precision and recall. We tried to manually label the images. So we tried to sample 100 images and measure within the peers on the classification. And we also use the human error also can due to the visual ambition and also lights and the background clusters. So our human performance is around 95 to 97%. Our data set is coming from the Kaggle, which is around 8,700 images with vehicles and not vehicle images around 8,900 as well. The format of the data set is in PNG images, and we balance the classes as well. The image size is about 64 times 64 pixels from the model consistency, and then we split 70% of our data sets training, 15% as cross-validation, and the rest 15% for testing. And we classified one as a vehicle, class 0 as non-vehicle. Now I'm gonna pass to Xiaohui to discuss about our models.
So in our base model, we started by applying a logistic regression model without any hidden layers to our preprocessed image dataset. And the model was training using 1,500 iterations and a learning rate of 0.005. We plotted the cost versus iterations along with training and test accuracy. However, the cost plot was linear, which indicates that the model does not learn the features. So this result shows that logistic regression is too simple for our image data. So even when we were already flattened, next slide, please. So to improve our model, so we use random search to turn the hyperparameter, and based on the result, the best compilation was the number of neurons is 45, and the learning rate we choose is 0.01. So we will use these values in our base neural network model. Last slide. So our original model has the following structure: a flattened layer to convert the image input into a vector, a dense hidden layer with best neural units using ReLU. So a second dense layer with 4 units, and a sigmoid output layer for binary classification. So the model performed well, but showed minor overfitting, as the gap between training and validation accuracy was occurred. So last slide. So we test 3 learning rates, which is the 0.01 and 0.003 and 0.0005. So a learning rate of the 0.03 gave the best balance between fast learning and model stability. So last we test 3 different optimizer, SGD, ADAM, and IMS prompt. So all using the same learning rate 0.01. So ADAM performed the best with 93.21% validation accuracy, And the second is IMS Prom came second with 92.15%, and SGD performed at 88.7%. So this shows that the choice of optimizer can affect model performance. That slide. So this, so we trained the model with 20 and 30 and 50 epoch to study how training terms impact performance. So the 15 epochs give the highest validation accuracy. So since the accuracy improved as we increase the number of epoch up to 50, so there is no sign of overfitting, which suggests that early stopping or careful training help the model generalize well. So 15 epoch is the optimal choice for this setup. So next slide, please. So in this section, so we compare three weight initialization strategy. So which is random, HE, and global uniform. So those three strategies give us similar results, but random uniform achieve the highest validation accuracy, followed closely by the other two. So this indicates that our model is robust to different initialization, and initialization is not a limiting factor in this case. So we have completed the base model setup and test several optimization techniques. So next, I will hand it over to Jack, who will explain the advanced models and evaluation, including CNNs and pre-trained models and more.
Great. So continuing on with some of the other models we tried on L2 regularization, we found that a lambda of 0.001 resulted in the best validation accuracy of 92.05. The larger the lambda got, the lower our accuracy became. Um, Moving on to dropout regularization. Uh, Next slide, Max. Thank you. We tried several different dropout rates and found that zero point 0.3 gives the best training and validation accuracy. Again, the higher the dropout rate became, the lower the training accuracy, which also resulted in lower validation accuracy. So a dropout rate of 0.3 was the best for us. Combining these two methods, dropout plus L2 regularization, we were actually able to get a 93.8% validation accuracy by combining those best two dropout rates and L2 regularization lambda values. Um, when we tested batch normalization, we found very high training accuracy values with marginal increases in validation accuracy up to 94.99% validation accuracy using custom parameters. Um, Continuing on to early stopping, we found that early stopping prevented overfitting or reduced overfitting that we saw in batch normalization, but resulted in a slightly lower validation accuracy of 93.21%. Early stopping, when we combined it with our best optimizer, Atom optimizer, batch normalization, and dropout plus L2, resulted in our best overall custom model. When we moved on to convolutional neural networks, um, we saw again another increase, a huge increase in our training accuracy, with a small increase in validation accuracy to 94.43%. And this is due to the convolutional neural network's ability to capture spatial hierarchies and reduce the underfitting and overfitting, overall making it better at generalizing on our data set. When we tested a few different pre-trained models, we found that the MobileNet V2 gave us by far the best validation accuracy of any of the models we tried previously, um, beating our CNN model by about 5%. So 99.84% validation accuracy in our binary classification data set. The transfer learning combined with the pre-trained model significantly boosted validation performance and gave us nearly perfect accuracy. Um, the RNN models did not do nearly as well, given that their primarily used for sequential data, but they still perform similarly to some of the custom models that we had been training before moving on to the CNNs, with the highest validation accuracy of 92% on the RNNs. Uh,
So let me walk through our best model, the pre-trained MobileNet V2. As shown in the summary, this model achieved outstanding performance with a validation and test accuracy of 99.84%, along with a recall of 99.81%. The confusion matrix reveals an almost perfect classification. Only 5 out of 32,000 test samples were classified. This indicates extremely low false negatives, no signs of overfitting, and excellent generalization across unseen data, making it the most reliable among all models we tested. Next. From a managerial perspective, such performance translates into multiple operational and strategic advantages. Compared to logistic regression, this model boasts accuracy by nearly 29%, which is critical in high-stakes contexts like autonomous driving or traffic enforcement. Its ability to automate vehicle image classification helps reduce manual workload and is scalable to large-scale camera systems. Because of its lightweight design, it can also be deployed on edge devices, reducing infrastructure costs. And moreover, this improved precision and recall enable smarter data and for city planning, traffic monitoring, and real-time decision making. Next. So in conclusion, our model offers both cost saving and revenue generating potential. A misclassified vehicle can cost between $100 and $300 in manual labor or follow-up actions. With this model's high accuracy, we can prevent around 20 errors per 10,000 images, resulting in estimated saving of 20,000 to 60,000 per dollars per batch. On a larger scale, deploying this model across 1,000 camera nodes and avoiding even just one error per day per node could result in over 1 million in annual savings. Overall, the model not only improves detection quality, but also offer a compelling return on investment for smart city applications. Thank you.